you have it, two of my major interests in life, photography and archaeology, both intersect with this particular research. So I'm proud to be sharing this here with you today. The petroform that prompted this research is called the Penokee Man, and as I'll show you, he is a unique cultural resource that is tailor-made for a study of this nature, in our opinion, and we are fortunate to have stumbled upon it. It is certainly the only one of its kind recorded in Kansas or on the Southern Great Plains, from what we can tell. And before I get too far into what it is, let me define a term I'll be using often that you may not be that familiar with. That is the word itself, petroform. A petroform is basically a similar term for a rock alignment or a stone effigy. The term petroform can also include narrative figures, shapes, or groups of rocks within the class of rock art that we generally call petroform. In this particular case, the petroform we're looking at is a stone man, which measures 57 feet to head to foot in length and 32 foot in width. It's comprised of individual silicified chalk stones, which measure between 5 and 20 centimeters each in diameter. And to better document and understand this petroform, we designed and conducted a UAS, or drone-based photogrammetric study of the site, which is located in Graham County, Kansas. As you can see here on the map, this is in Google Earth Pro. Just to kind of point this out here, the button here. This area here is where the site is visualized, and you can see its scale here. This is a 1 kilometer resolution from the 2014 September aerial imagery. It's available on Google Earth. And what we were able to visualize is inside that red box. But I just kind of want to pull out to give you a perspective there. Back in March of 2015, we were lodging at a cabin on the ranch where this is located. Mary Goddard, who is one of the landowners, had told us that she had a stone man on her property and had offered to take us for a visit. She described a large stone man in the form of a rock alignment with a spear and shield laid up on top of a hillside. As you can see here from the photo, north arrow is directed. The petroform itself is located here. You can see one rock right there, but it's in this area. So we were excited to visit, but at first we really didn't see anything, and it became clear that we were going to have to develop some sort of method to visualize this all in one place. When we actually did see Penokee Man and do a visit and walkthrough, we realized that we needed to document the composition and the condition of the petroform itself, and also became clear that there was more to the site than what we could see from readily standing on top of the hillside. Sorry. Okay, so what we know about the site. This image you see here on the left is from the National Register of Historic Places eligibility form, which is a sketch map which has all the comprised stones. As you can see, it is a stone man. There isn't a spear or shield visible really here, but he is most definitely a man. When we visited the site in March of 2015, we counted 122 visible stones on the surface and captured ground-based photographs. When we tried to locate the petroform from aerial and satellite imagery, we encountered our first problem, which was namely, where is Penokee? And it's in this red box here that you can't see. You can faintly see a little bit here in his legs, but we couldn't get good resolution even with Google Earth Pro or some available stuff to see him in a way that we could visualize. So examining the visual record of the site, we find that there is a gap present between the available space-based or satellite imagery and ground-based photography. When we tried to photograph this petroform on the ground, we found it difficult to visualize. We realized there was a need to generate imagery which better documented the site fully. To this point, I'll just make a little reference here to this photo here, which was taken in 1974. This was the only known aerial photograph of the site itself, and it was taken by an FBI agent who regularly flew back and forth on a private plane. And it's a bit poetic, but I'll just give you a quote about this because it's relevant to how difficult visualizing the site was. Mr. Piper said, "Regardless of how many times we flew over it from different directions and altitudes, it always remained invisible to us, as if the stone man was hiding in place and didn't want his resting place revealed. One afternoon, we flew over the stone man's home, and the plane was just as the setting sun was touching the western horizon. And wonder of wonders, he was at home that evening and made a grand appearance on the high field overlooking the Solomon Valley. Every stone in the outline of his worn and weary body glistened and sparkled like diamonds. His upraised arms seemed to be waving and giving a warm welcome. He was truly a chief that evening." So a bit poetic, but as you can see, it was difficult to see, and this guy had flown over hundreds of times, and this is the first time he was able to get a photograph. We had the same sort of experience. This is a table which kind of gives you a history of the site itself and what we know. And we started by compiling what we could find out of the history. The column I want you to key in on here is right here highlighted in green. 150 individual stones were visualized from the aerial photograph as reported. In 1982, when they actually performed the site survey and the NRHP eligibility determination, they counted 168 individual rocks. which brought us to our second problem, is how do we get an accurate count of the individual stones and elements at the site, and how do we visualize the site in a way that allows us to track the change that may have occurred to the site over time. So we had two questions and two problems. Number one, how do we visualize the site in a way that can resolve the imagery gap we've seen between aerial and satellite photography or imagery versus the ground-based photographs? And how can we see better what's actually there? And second, how do we document the composition of the site and the condition of the petroform itself in a way that can tell us what possibly is missing or may be hidden to us from the ground? So, our proposed solution was to use a photogrammetric solution, which required us to develop a low-cost and our close to free as possible UAS system and mount a high-quality camera to conduct a photogrammetric study, which was able to fill the gap between the space-based and ground-based photography. Our desired goal was to generate useful photogrammetric data to visualize the site. This included goals of being able to output orthomosaic photographs, georeferenced DEMs and contour maps, which were comparable to LiDAR, and our goal was 5 millimeters per pixel as a resolution. So before I get too far into the photogrammetry thing, for those in the audience who aren't completely familiar, oops, what's going on there? Oh, sorry, wrong buttons. What is photogrammetry? Quite simply, photogrammetry is the science of making measurements from photographs. The output of photogrammetry is typically a map, drawing, measurements, or a 3D model of some real-world object or scene. Many of the maps we use today are created with photogrammetry, and photographs taken from aircraft or satellites. And in this case, we developed a custom-made UAS or drone in order to capture this data. And just for fun here, this is from an old textbook here. You can see this is basically stereo vision. You're taking two images and you're looking at it straight 3D from 2D. The image you see next to it is sort of how the computer computes that in with the software and takes the still images and builds a 3D rendering from it. So the design itself for the drone and for the study itself required a structure from motion based design, which basically meant we were going to generate point clouds, the 2D translating into 3D. We used a rule-based data acquisition method following the structure from motion, which did this. Again, our goal was to try and generate 5 millimeters per pixel resolution. The design and build of the drone itself took about 4 months, and the UAS we designed was built for the purposes and tailor-made to mount a high-quality DSLR camera on board. In this case, we chose a Sony Alpha 5100 mirrorless DSLR with a 30 millimeter lens, prime lens, focused at f2.8 aperture, and it shoots at a 25.6 megapixel resolution. It's a little bit heavier than the typical cameras you'd see on drones, and so we basically built the drone around the camera. The camera was the most expensive part of the build. Most of the parts and the components were pretty low cost and widely available online, including the 450 millimeter size airframe, the internal measurement unit, the autopilot, which you see down here in the bottom, and the GPS and sonar modules we added in order to kind of correct it in flight. We also opted to use Photoscan Pro and QGIS to process and render the data from the 3D point cloud into mapping itself. There's also some free resources we used, Google Earth Pro namely, and ArduPilot Mission Planner, which ran the software that controlled the APM itself. And as far as paid resources, AgiSoft Photoscan Pro is a paid software, but we managed to process the data within the 30-day window of the free trial. So our total cost for the project was $1,250, and by February of 2016, just 2 months ago, we were able to put our work to the test. And this is conducting the photogrammetric study. It was very cold and very windy. As I mentioned, in Grant County, Kansas, this is sort of the highest hill in the county. So when it says it's 20-mile-an-hour winds, it's probably 35-mile-an-hour winds. As you can see here, the drone itself is right over the top of the petroform, and from the ground you can't see it. Again, this is another reason why we thought developing a solution would be useful. The results of it were these generated images. As we flew the drone, we exported everything to AgiSoft. What you see here at the top left is the sparse cloud that we created from the sorties. These points are the focal plane of the camera itself that it's flying over. One note for the drone enthusiasts out there, a lot of these times you'll see grids over the top of sites. Because of the wind, we weren't able to have a grid. We were having to fly it on manual, and so we had a little bit of skew with our aspect there. But we were able to generate, in this image here, a dense point cloud which composed 18 million individual points. From that, we constituted the basis of a wireframe mesh, which we generated a texture from. And here we selected points by color and location to highlight key points for the model to build from. And here in blue, you can see those key points which the processing outputted. So our question 1 was answered by generating a textured orthomosaic image composited from the point cloud data. And even though it's a bit rough and difficult to visualize, you can see clearly he's here with the vegetation skewed out, his head, torso, chest, or waist here, and his legs. So we were actually able to meet our first goal, which was to actually visualize it in one image. The second goal was to generate 1 centimeter interval contours of the study area. We were able to do that to establish a baseline for the search conditions and to highlight change and disturbance of the petriform itself. And these changes and disturbances, once we were able to document it, were all just outputted from the point cloud itself. So, the results. Observed impacts and disturbances. What you see on the left is a representation from the initial sketch map in 1982. What we've done here is just highlighted in the middle the ones that we were able to detect that were gone, both in 2015 in our visual study and in 2016 from the photogrammetric study on the drone. There's some 4 green rocks here that are also disturbed but not missing. We think they're probably part of the petriform formation itself that may have just been knocked out, but we can't account for it, so we have 3 different classes of rocks. White represent what's present now, red is what's missing, and green looks like what they're altered. The likely causes for this, we know that they're grazing livestock on the property, and so it could be cattle that are disrupting. And what you can't see in here, but you can see in some of the higher grade visualizations from the mesh, are truck tracks that come right across here and across the top. So we do have some evidence now of mechanical and animal-based disturbance to the site. So what we were able to do is fill in this table and add our efforts to the bottom. In 2015, we counted 122 rocks. In 2016, the photogrammetric study identified 122 rocks. So it was kind of paired there, but we do know that we're missing quite a bit from the initial sketch study that was done from 168 to 122. There has been something going on there at site. Whether or not these rocks have actually been removed or whether or not they've been subsumed through erosional processes, as you can imagine, these rocks are very flat and close to the ground, so it's on a high plane. Erosion may be layering sediments on top of these rocks. They may be there and just below the surface. Because it's private land and because it's sort of outside the scope we want to do at this point, we haven't done any kind of ground testing. Maybe that's for future work, but we want to be able to track and see where these things are for sure. So our model, we did fall short of our proposed goal. The 5mm per pixel resolution, which is in part derived from the study of Nolte in 2012, and Tom Noble did the comparative LiDAR versus point cloud project in Denver, Colorado. We achieved a 5.16mm pixel accuracy over the 505 meters square visualized area within the point cloud, which is comparable but not quite as good as LiDAR. We were able to detect both changes and disturbances to the site and compare our results to early accounts of the sites, both contemporarily and historically. These data have created a baseline for future site monitoring and preservation, and the methods and techniques adapted for this project could provide useful lessons for future research. And now that we have visualized and accounted for the elements comprising the petriform itself, our future research will focus on the bigger question: what is Penokee Man, and why is he some 250 miles further south than any similar petriform on the Great Plains? And in conclusion, I'd just like to give thanks and appreciation to the following people and the outstanding efforts that they put in to make this research and presentation possible. Thank you.